Hello everyone, we are Group 43 and this is our video showcasing our application for the AGISIT project. So, we start by showing that in our Google Cloud dashboard there are no VMs or disks currently running. And in our code, we can type the command just start to build the monitoring container and run the container with the command just monid. In the container, the command just deploy can start the deployment of our application. As we can see, the machines are already appearing in Google Cloud. The application is already deployed, as we can see on the Google Cloud dashboard. So we can start by opening the application by pasting the front-end public IP in two different pages. Right now, not all pods were already available, so the new user couldn't register just yet. Now we can create our accounts. In the first window, we'll create user 1 and log in. In the second window, we'll create user 2 and log in as well. And now from user 1's page, we'll start a new conversation with user 2. Let's send a message like hello and how are you? As you can see, user 2 immediately receives a notification. Now, if user 2 opens the conversation, they can see the message and reply, maybe, "Hi, I'm fine." Next, let's test the group chat functionality. We'll open a third browser window. Here, we'll create and log in as user 3. Going back to user 1's page, we can create a new group. Let's call it New Group and add both user 2 and user 3 to it. Now, user 1 can send a message to the group. Both user 2 and user 3 receive it and can participate in the conversation. Let's send a few more messages between the three users. Okay, now let's simulate user 3 going offline by closing their browser page. With user 3 offline, let's see how notifications are handled. From user 1's page, we'll send a direct message to user 3, something like, "Hi, where have you been?" And from user 2's page, let's also send a message to user 3. Now let's open user 3's page again and log in. As you can see, user 3 has notifications for both the message from user 1 and from user 2 that were missed. We also set up monitoring for our application. Let's open our Grafana dashboard. Here, we can see various metrics about our application performance, like CPU usage, memory, and network traffic. We can also see those metrics for a specific service, for example, the authentication service. We also have a benchmark script to simulate load to the login page. By updating it with the IP and a user from this deployment, we can test if our application can handle 1 to 1,000 concurrent login requests using the hey command. As we can see, all of the values, for example, the HTTP request duration, has grown linearly and did not crash or time out under stress. A key feature in our project is persistence. To test this, we'll first destroy the application using the just destroy command in our monitoring container. If we check the Google Cloud Console, we can see that the VMs are being terminated. But importantly, the persistent disks containing our data remain. Now, let's deploy again the application using just deploy. Once the application is back up, we'll log in as one of the users, let's say user 1. And as you can see, all the previous conversations and messages, both direct and group, are still there, proving our data persistence works. Finally, to clean everything up, we'll run just destroy one more time to delete the application. And then let's delete the persistent disks from the Google Cloud Console. Now we can confirm that all resources have been successfully deleted.
In this next part of the video, we'll be covering the general architecture of the application. Starting at the entry point, we have HAProxy, which acts as the system's front end. It's deployed behind a Kubernetes node port service, making it accessible from outside the cluster. HAProxy's role is to receive all incoming client requests and distribute them evenly across the Nginx web server replicas, ensuring load balancing and reliability. The Nginx web layer serves as a reverse proxy and API gateway. It runs 2 replicas for high availability and routes traffic to the correct backend microservice based on the request path. For example, /auth requests go to the authentication service, while /chat requests are directed to the chat service. This separation keeps the system modular and scalable. The authentication service is built with Flask and handles all user management operations, registration, and login. It connects to its own PostgreSQL database, called AuthDB, where user credentials are securely stored. Sensitive configuration values, such as database passwords, are injected through Kubernetes secrets, and the database itself is backed by a persistent volume, ensuring data durability even if pods are recreated. The chat service, also developed in Flask, manages the core messaging features, including direct and group messages, message retrieval, and group creation. In the final version, we added a notification subsystem that tracks the number of unread messages per conversation, improving user experience. Like the authentication service, it's connected to a dedicated PostgreSQL instance called ChatDB, which permanently stores all message and group data. Both databases, AuthDB and ChatDB, run as independent Kubernetes pods and are backed by persistent volumes provisioned via the GCPCSI driver. This ensures data remains available even if the pods or nodes are restarted. Separating each service's storage increases reliability, simplifies maintenance, and supports independent scaling. Overall, this architecture demonstrates a fully containerized, cloud-native application, scalable, observable, and reproducible through infrastructure as code. It effectively separates front-end, back-end, and storage concerns, providing a solid foundation for further improvements in security, scalability, and real-time communication.